Well, thanks everyone for meeting in the midst of a pandemic, and for the Oxford organizers here, both inviting us as well as carrying on, keeping calm, and seems to be going quite well so far. So I am a close neighbor of Stephen DeCalliway. He's at School of Mines, and the M, which is on his mountain, is, I think this picture is reversed, but somewhere up there, my hand's disappearing. NREL doesn't normally look quite this green, but around the month of May and June, it's about this green, and then it kind of turns brown later in the summertime. It's kind of an arid climate. We're in Colorado, close to Denver, Colorado. So what you see on the screen here is a high performance computing image of microstructure of an anode. It's a little kind of cubed. It's not a very fine representation. And those are flux lines of the lithium ions traveling throughout the electrolyte. We've got quite a group, both past and present here, which there's much material. I'm sure you could ask some difficult questions that will break my knowledge, but look forward to the discussion later on. And I'd like to acknowledge all of the co-authors on here. There's quite a bit of work from quite a few people, including a few that have recently left our group, Weijie Mai, as well as one that left several years ago, Gihan Kim, who was quite foundational in forming the KBAT program. Okay, so to start with a slide from Department of Energy, this is our program manager, David Howell's slide. Motivating. Got a little bit of feedback. I'm not sure if that's from me or someone else. There we go, I think we're good. As we continue down the cost curve with graphite high voltage NMC, it will be, and let me switch to a laser pointer as well. Hopefully this is working. Yeah, okay. Of course, that's going to plateau at some point. And so we really need to move to future chemistries such as silicon, which has less material because silicon has a higher capacity to it, to go further down that cost curve. And then leapfrogging that, transition to a new technology such as lithium metal or lithium sulfur. And so presently lithium sulfur, for example, has a lot of excess electrolyte and just a really small volume of sulfur. And so that needs to be reduced greatly, and hopefully computational models can help with that reduction to get us on a pathway to where at the pack level, we can reach about $80 per kilowatt hour. I think some common modeling says that around $100 per kilowatt hour is kind of a tipping point where at least modestly sized conventional vehicles or modestly sized electric vehicles are cheaper than conventional vehicles. This is a lot of the different activities in our group: battery material synthesis and processing, component testing and characterization. Our test labs are known for their isothermal calorimeters. There's some custom equipment, which I think you can purchase from NETCH now, which has been licensed through NREL. And then getting into topics that I'll cover in this presentation: the multi-physics battery models, some battery management and control, especially lifetime models. And then this plugs into analyses that go on throughout the laboratory, both for the grid and for automotive utilization, to determine what the most cost-effective and technically smartest pathways are for advancing electrification of our transportation and our grid as well. Okay, the outline here, I'll talk mostly for the overview about the KBAT program, which stands for Computer-Aided Engineering of Batteries. Then I'll get into a couple of modeling examples from our Extreme Fast Charge program. And then more recently, we've been working a lot at the microstructure level, both characterization, understanding what the role of microstructure is and how that influences battery performance, and then also simulating the electrochemistry directly at the microstructure level. I'll say a few words about how we're working to integrate solid mechanics and degradation into that model. It's not straightforward at all. Next, do a little bit on silicon anode modeling, some of which Stephen covered already. And then finally get into the lifetime predictive models, which are more at the systems level, and there's less physics in those models. Okay, for the overview here, I'll talk a little bit about physics and then the multi-scale models. I think I can quickly skip through. Everyone knows what what the common materials are in the electrode pair and how the cell is constructed, filled with electrolyte. So here comes this slide speaks to the complexity of lithium-ion batteries. There's so many different physics ranging from the atomic scale up to the system scale. And at each of these different length scales, it might take a separate model to consider what's going on. There are important trade-offs to consider across these different length scales. For example, how your electrochemistry is influenced by the localized temperature within your battery cell or your battery pack. So it does make sense to couple some of these length scales. Other things I like to say about this slide is that each of these different categories oftentimes is a separate academic discipline. And really the breakthroughs are going to come through multidisciplinary research where we talk together. And I think computational models are an efficient way for us to kind of communicate the different trade-offs across the different length scales. So one work that Gihan Kim led back in 2010, 2011 time frame, and this kind of kicked off the KBAT program, was to take the common P2D Newman model, which solves for reaction transport physics at the particle domain and at the electrode domain. That's already a multi-scale model. And then to carry that up to the cell domain. And so at the cell domain, the new physics that occur are the electron transport, so potential gradients that occur throughout the current collector foils as the electrons have to travel from an inner region of the cell all the way out to the terminals. And then also heat transport, where heat has to travel from the center of the cell where it's generated out to the edges of the cell. And some work had been done already in this area. I think John Harb had some papers well before this. But kind of a unique contribution that Gihan came up with is that you don't have to exactly resolve every single current collector. You can treat the cell as an orthotropic cell composite medium with isotropic properties. With anisotropic properties, orthotropic properties. They have a directional component to them. And so what you have then is a vector that describes the electronic conductivity in the direction of the current collectors. And then also a tensor, and a tensor that describes the thermal conductivity as well, which is preferentially in the current collector directions. And so with this, you can build up models that represent the common configurations of cells: a stacked pouch cell, wound prismatic or wound cylindrical cell. Depending upon the configuration, you can potentially, instead of having this single potential pair continuum, consider a dual potential pair continuum, which captures the more intricate design when you have a wound cell and there's two cathode layers, for example, on each aluminum foil layer. Moving into the kind of the initiation of KBAT, so this was about in 2010, I believe, that this was kicked off. DOE and industry, they really recognized that there was a gap in missing tools that coupled together the electrochemistry together with the CFD tools, which solve for the external flow field and the cooling system on the outside of the cells. And so with these first generation tools, within a couple years, some of these were already off on their going before this DOE program. Others got started under the DOE program. There's 3 tool sets, and then another large one, which was not part of this program, but equally capable COMSOL, can solve the electrochemistry coupled with the heat transfer problem and the flow field on the outside. Some focus areas for KBAT 2, one is recognizing that the Newman model has a lot of parameters in it and they're pretty tough to identify. We did some work on parameter identification. I'd say this is only partially done. There's still definitely much to be done to kind of improve the utility of the Newman model in terms of once you get a new chemistry to identify all the parameters. That said, it's quite common that this electrochemistry, instead of being represented by a Newman model when you scale up to the 3D cell domain or 3D pack domain, people oftentimes use a surrogate model, such as a circuit model, and thereby avoid the difficulty of identifying all the Newman model parameters. But there definitely are studies where it's necessary to have the full Newman model. And then we've also been doing a lot of work. My colleague Shriram Santhanagopoulan leads an effort in mechanical abuse. And so this is modeling what happens in the case of crushing a cell. And so for instance, under a vehicle crash scenario. More recently, under both KBAT and the Extreme Fast Charge program, we've kind of delved to the lower length scale, and we've been working on microstructure and understanding how that influences battery performance. I just have one slide on the safety and abuse models before I continue on with some of the other things, such as the microstructure models. So our first models were simply 3D thermal models. There was no electrochemistry or electrical pathways within the cell, following on some of the work of Jeff Don to describe the kinetics as a heat source term. And so you can see if there's a hot spot locally in a cell here, how it spreads throughout the cell just based on the directional preferential conductivity through the foils. The foils are in a wound structure, so it goes around the circumference of the cell. And so you can see the propagation going both in the circumference of the cell as well as vertically in the direction of the foils. And so that describes the evolution throughout a cell, and it can be important to know how that evolves so that you can potentially evaluate safety features such as shutdown separators that melt at certain temperatures. And then this carries up to a module or a pack level, and so you can simulate cell-to-cell propagation. And depending on how patient you are to match up thermal contact resistances and such, you can get very tight agreement between the experiments and models. And one can imagine that blowing up a pack or a module is a very expensive experiment. After the fact, it's been burnt to the crisp. A lot of times it's difficult to determine the sequence of events, and so models are very useful for helping to determine the sequence of events. Following up with that, we've done some work to use accelerated rate calorimetry and calibrate the heat source models to that. And then with the KBAT, the 3D electrochemical thermal models, that's what ECT stands for, we now have a description of the 3D electrical pathways within the cell. And so you can consider things like what happens if the separator wears out and you've got something that looks kind of like a field failure, versus what happens if you have a more catastrophic failure. Some of these test methods, such as nail tests and pinch tests, aren't necessarily representative as to how the cell would respond in the case of a field failure if there's a defect within the cell. And so models are effective at taking test results, interpreting those, and extrapolating them to a different scenario. And then, like I mentioned, the mechanical crush models. So it's very instructive to determine what the sequence of events is for failure. In some cases, you could see cell failures and including the internal components of the cell. In other cases, it's module components, bolts and such that fail in detailed sequences of events. This is a very complex model. It's presently in LS-DYNA. There are some electrochemical thermal couplings that Sriram has built into that model, or you can take a deformed geometry and import it into a CFD model such as ANSYS or STAR-CCM Plus or COMSOL and simulate the safety abuse response once you've got a deformed geometry to start with. So that's the kind of the safety models. Some of the things that we're working on is better understanding all the damage modes, characterizing the materials, especially at high strain rates. It's difficult to test at the very high strain rates that you see under a vehicle crash scenario. Okay, next I'd like to talk about a couple examples from the Extreme Fast Charge program. And I'll mostly talk about macrohomogeneous model or Newman model results, which kind of describes the average response of a cell and gives you a little bit of indication of the chemistry and what the limitations are. But it's also very important to understand the heterogeneous response, and we feel that that's what drives degradation, or at least the early onset of degradation. So this is some work published by Andrew Kolklaser, and we've been working with multiple labs. So Idaho National Lab, Argonne National Lab is building test cells. Lawrence Berkeley National Lab is doing diagnostics, as well as SLAC. And so we've got multiple different loadings of cells that Argonne has built. And so if you have very thin electrodes or a low loading, 1.5 milliamp hours per centimeter squared, this type of cell is very extreme fast charge capable. And so you can see we're going up to a 10-minute charge 6C rate with no problem here. Whereas for the, as you go to a higher loading, and this would be a cell that perhaps is around maybe 180 watt hours per kilogram, so decent energy density, you can only charge at a 10-minute rate, 6C rate, up to about 35% state of charge before you hit a cutoff voltage. The big limitation here is in the electrolyte transport. And so you can see that under all of these simulations here, all the way up to a 9C rate for this thin electrode, you're not reaching the electrolyte depletion condition. Whereas once you're doing 9C rate for the thicker electrode, the 2.5 amp hours per centimeter squared, here you're hitting electrolyte depletion in the back part of the electrode. Once that happens, only the front part of the electrode is active. And so whereas you might be charging at a 9C rate, on average, the front part of the electrode might see perhaps a 30C rate at the very front. And so you very quickly saturate the surface of the graphite particles and then start with the onset of lithium plating. And this is a key thing that any reduced order model that's interacting with a control strategy for fast charge has to be able to predict is the electrolyte transport limitation. And it's highly nonlinear. Some of the work that I did for my PhD thesis was to develop reduced order models that were very linearized. And I think those are not suitable for this particular condition. So that's something that I encourage all of you control-oriented modelers to make sure that your model matches up closely with the full order model under that condition. So with this knowledge, Andrew has taken the model and scaled up to higher energy densities, 3 milliamp hours per centimeter squared. I think now we're in excess of like 200 watt hours per kilogram. The baseline cell could only charge at a 6C rate if it hits to the 4.1 cutoff, just to like 30 watt hours per kilogram. So that's pretty shoddy. If you do things like reduce the tortuosity to improve the effective electrolyte transport rate, you can do better. If you go to modestly elevated temperature, 45 Celsius, or very elevated temperature, you do a lot better. So the electrolyte transport gets a lot faster at these elevated temperatures. And so really what we feel is necessary with present technology is to do a combination of reduced tortuosity. So this would be things like having secondary pore channels in your electrodes, or aligning the particles so that they stand up vertically in the electrode instead of laying flat in the electrode, as well as the elevated temperature. Or the best solution here would be to have some next generation electrolyte, which doesn't exist yet, and this is a tall order, but this is also a research effort under the Extreme Fast Charge program. And so Andrew has identified some requirements that you have to roughly double the conductivity, have about 3 times the diffusivity, and also modestly increase the transference number. So with that, we could have both energy dense, 10-minute fast charge capable batteries. Okay, getting into the heterogeneities just a little bit. This is kind of a high, high viewpoint here. There's a lot of different length scales that are involved, ranging from the grains and particles all the way up to the cell level effects. And to point out a couple of these, all right, at the grain level or particle level, this is a depiction from Steve Harris, both for modeling, depicting the individual grains, and they each have different crystalline orientations. And so some of these crystals are going to face towards the outside of the particle. Others are going to have the basal planes pointing towards the outside of the particle, which aren't facile for transport. And so with this, you can kind of see in optical images that there's localized regions which are preferentially intercalated. The brightest spots are the ones that are intercalated the most. And so there's definitely some heterogeneities here. And indeed, if you continue with these optical images and further into the charging, you definitely see lithium is plated preferentially at certain regions in this electrode. These are things that we're working to understand under this program to see how we can best suppress this. The Newman model just gives us kind of the viewpoint of the electrode thickness heterogeneity that I described on the previous slides. Some other factors across the electrode coating, either at the hundreds of microns, maybe to millimeter scales, there's going to be variations in both porosity and thus tortuosity across the electrode. And we feel that this is leading to preferential areas of lithium plating early on. We've done some modeling together with Purdue University. Dean Wheeler from Brigham Young University is part of the project now, and he has some methods to characterize the tortuosity locally across electrodes. So we'll be looking to validate the models for that. And then we haven't yet spanned up to these length scales, but at the cell level, there's additional heterogeneities. And these are some images from Ira Bloom at Argonne National Labs. It's an unrolled jelly roll. You can see that the preferential plating has occurred, I believe, at the center of the jelly roll, as well as the center of the height of the electrode. And we don't yet have good models that describe this. It's probably some combination of hotter temperature causing preferential utilization of the center part of the electrode, together with maybe some edge effects of the electrode. So all of these things need to be better explored in order to better understand how to design a good quality fast charge cell. Okay, now moving down in length scales to the microstructure, I'll describe some work that we've done in tortuosity estimation. We've got some tools which are either on our website or coming very soon. So this is a paper we published 2 years ago. This is led by Francois Useglio-Verretta, and he has done all the microstructure modeling and homogenization calculations. So there's a lot of different discrepancy in what is the correct tortuosity for a given electrode, what type of microstructure, what are the microstructural influences. And so we did some work with 3 different methods. So here we have CT images from Paul Shearing at University College of London and his group. Unfortunately, those images do not include the carbon binder domain. You can do fib-SEM and resolve the carbon binder domain, which is what shows up in this green pockets between the red active material particles. And so instead, we relied on an algorithm from Purdue University, which has numerically generated that. Dean Wheeler at Brigham Young University has followed up with direct measurements. And then also Andrew Kolklaser has done some estimations using the macrohomogeneous model, fitting tortuosity to actual data with rate limitations. And so we've compared all 3 of those. They do compare fairly well. In the case of so this is an NMC material with more or less spherical particles. This is a platelet-like graphite material. The orange here are the macroscopic models. Here we have a lot of noise in the macroscopic models because at low tortuosities, you don't see much rate dependence on tortuosity. It's other things like solid state diffusion that consider it. But we do see great agreement between the experimental measurement from Dean Wheeler as well as our estimation from the homogenization calculation or the microstructure modeling. Here at the higher end of things, we get fairly good overlap amongst all of the different methods. There's definitely noise across all of the methods, but we think this goes a long way to showing what the different sources of error is, and Francois has done a great job at describing all the different sources of error in the paper. These different materials, the graphite and NMC, we had 4 different electrode thicknesses and calendared and uncalendared electrodes that we tested. And all of these are available in this microstructures library to be freely downloaded. For this one particular graphite, it's kind of a platelet-like graphite, and so it has high tortuosity. There are other better graphites, such as this particular superior graphite, which has more of an ellipsoid or potato-shaped. It's still not quite spherical, which has a much lower tortuosity. And so particle morphology and orientation play a really strong role. In order to kind of decouple all of this, Francois has worked with all the CT images to deduce the particle size statistics, as well as the different factors, geometric factors, which contribute to tortuosity, such as constriction of pores, where you have a smaller constricted area, as well as particle orientation. And in order to do this, he's had to come up with his own method of identifying each of the particles from a CT image. Some of the previous methods, such as watershed, would poorly segment the particles, such as this one that's circled in red. You can see what we feel is clearly one particle represented in purple over here is broken into 2 separate particles. So in order to get correct statistics, you definitely have to do a good job of identifying the individual particles. And he's submitted an article. Hopefully this will be out in the next couple months on this method. But with that, one of the key metrics that he came across to help correlate with tortuosity, and this seems to work across all these different materials. Here we've got 1 NMC material as well as 5 different graphite materials. Basically, the sphericity is very important, but if the particle is not spherical, the metric that he's come up with is particle elongation in the through plane direction versus the in plane direction. So you can imagine if you have platelet-like particles which are aligned in plane, then you're on this part of the axis. If you have platelet-like particles that are stood up straight, then you're off this axis to the right side here and have very low tortuosity. And so with this, he's come up with very good correlations that describe for any arbitrary material a prediction of the tortuosity. Moving forward with microstructure analysis, he has an open source toolbox, which we hope to post online in the next 6 months or so. And so it characterizes the microstructure, does homogenization calculations, plugs in with ISO2 mesh to do meshing of the microstructure, correlates different parameters and statistics. You can select a region of interest that you want to work with, do some filtering, contrast correction, segment the electrodes. So we feel like this is a great tool which will help with kind of standardizing the workflow of lots of different researchers and hopefully help us all to build up libraries that we can share as well. Next, I'm going to get into the direct numerical simulation of the 3D microstructure. Our numerical approach, exploring the heterogeneities, what causes early onset of lithium plating on fast charge, and how we can potentially design some new electrodes to avoid that. Okay, kind of for tutorial value, here are the governing equations, and similar to the Newman model, but recast a little bit differently because porous electrode theory is no longer in play. Here we've got a direct description of where the electrolyte pores are versus the active materials. And I think this is very similar to what you'll find in other papers. And our method that we are solving here, we've done some work to directly solve all 3 domains simultaneously, the cathode, electrolyte, and anode. For us, it turned out the best, the most stable algorithm, and as well as the fastest, was to do a segregated solve. And so here we are solving each domain separately. So that's a linearized solve on an individual domain using the Newton method to converge. And then we have an outer loop of iteration to go until all 3 domains are self-consistent and everything is conserved. And we've done a lot of work. Jeff Allen, together with Francois, has a paper also submitted on this. Done a lot of work with our high performance computer to come up with what we feel are the best algorithms for scaling, both in a strong scaling and a weak scaling sense. And find that the hardest part of the problem to solve, again, is the electrolyte transport. And especially as you come close to electrolyte depletion, the system of equations becomes highly nonlinear, is difficult to solve. One convenient thing that he found, and I don't have this in the slides, is to recast some of the transport properties which go to zero when when concentration goes to zero. And some of the similar terms also show up in the governing equations. Perhaps I've got this in the governing equations here. I do not, but in this kappa D here, as concentration goes to zero, I guess in the natural log term, as concentration goes to zero, you have a singularity in this equation. You can avoid that if you actually just kind of recast your properties a little bit differently. And so that'll be in that upcoming paper as well. I think it would probably work well in a macro-homogeneous model. So where we are presently with the 3D simulations, we can simulate virtual microstructures or CT image microstructures. It's taken us a couple years to get to the point where we can solve this large of a volume in a full cell configuration, both a cathode and anode. And so these are the realistic microstructures. And we're about 4 times what we feel is a representative volume. So that's great. Now we can do things like consider additional heterogeneities. What if we put in a secondary pore network, drill holes through this electrode? What if parts of the electrode become delaminated from the current collector? How is that going to affect early onset of lithium plating? So those are some of the studies that are presently underway with this model. Some of the things that we have done looking at heterogeneities, we've done comparisons with the macroscopic model. So that would be the dotted line here. And we're looking at the potential difference between the solid phase and electrolyte phase, which is what drives lithium plating when you drop below zero for that quantity. And we see that in the microstructure model, there's localized heterogeneities that cause the plating to occur about 2.5% state of charge earlier than what a macro-homogeneous model would predict. And then we've done things like look at bimodal particle size distribution. So some manufacturers do this. They pack small particles together with large particles in order to get a larger, higher packing density, more volumetric, dense electrode. And we see that that increases the heterogeneity yet another 2.5% SOC. So a lot of these factors actually make the onset of lithium plating a little bit worse. But Francois did some work with the virtual microstructure generation tool, which is going in that open source toolbox, looking at different configurations of electrodes and how they contribute to the early onset of lithium plating. So here again, we're tracking that same potential difference. And so if you have misaligned electrodes versus spheres, that delays the onset of lithium plating a little bit later. If you align the ellipsoids such that they're pointing vertically from the current collector up towards the separator, that delays the onset of lithium plating even later. And so he's kind of plotted each of these. So this is the anode state of charge at onset of lithium plating, and found that he had to normalize versus the specific surface area of each of these electrodes. In a lot of cases, the specific surface area was slightly different. And as you go to higher surface area, that also delays the onset of lithium plating. So as we go up and to the right, that's higher specific surface area and delayed onset of lithium plating. He's looked at a lot of dual coatings, or you could also do this with a graded coating where you've got a different porosity close to the current collector versus close to the separator. And the best configuration that he's come up with, which Argonne National Lab is now building prototypes of, is a configuration where close to the current collector you have large particles and a low porosity, so very tightly packed particles there. And then the second layer, so you do a second coating layer after perhaps a first calendaring step with smaller particles, and you do this with a higher porosity. And so this type of electrode has a good balance of high surface area as well as a graded porosity. And you can actually have a similar surface area to if you had unimodal spheres and still get better performance from this type of electrode. I should mention that a practical consideration, you don't want to go too high in surface area for a real electrode, because the surface area scales with the rate of side reactions. And so your SEI consumption of lithium ions, for example, is going to double if you have double the surface area. So this is a good way of trading off both big particles and small particles, as well as different porosities. Okay, next, this gets into a little bit of our efforts on incorporating solid mechanics and fracture into macro-homogeneous models, standalone models, as well as what we'd really like to do is to incorporate this into this 3D microstructure model. This is still kind of a difficult task. We've got some early steps towards this. Working with Purdue University, they have a custom lattice spring model, which I'll describe. To finally resolve a NMC particle, right now we're working with an abacus cohesive zone model, describing damage just at the grain boundaries. And then also we're working on developing this and scaling this up into our 3D electrochemical model, which is in the Phoenix environment. Phoenix is an open source code, finite element based, which scales well on high performance computers. First, some goals of incorporating mechanics into the electrochemical simulation. We'd like to be able to describe failure modes of different materials and different architectures, understand physics and improve the materials, provide some feedback to the materials designers. Also, we'd like to have predictive modeling of lifetime, describing things such as material isolation, so that would be a loss of capacity, damage to transport paths, that would be a loss of rate capability, as well as evolving surface area, which gives you shorter transport paths. That's a good thing, and faster electrochemistry, more reaction area. But as I mentioned before, it also increases the rate of side reactions. Some of the challenges here are different descriptions of fracture and damage that exist in the literature, very different approaches that come about. And some of these we're not certain how high they'll scale in terms of the number of degrees of freedom. Our present microstructure model, when we solve that large volume of electrode that I mentioned, has about 25 million degrees of freedom. So first, the lattice spring model. This is a custom code from Purdue University, Professor Partha Mukherjee. When it has spring elements that represent the connection between each of these node points. And what they've done is to solve the diffusion problem in a separate model and then kind of port between these two different meshes, the mechanics problem due to volume expansion, which is in diffusion induced stress and such. So when any one of these bonds exceeds its limit, it breaks the spring, and then you inhibit solid state diffusivity or transport between those two different node points. The challenges here are porting this over to arbitrary geometry since it's custom coded, as well as scaling to 3 dimensions, though they have done some of this. But it's a very practical model, and so you can describe the behavior of single particles at different lithiation conditions. Such under lithiation, it predicts that you would have tensile stress close to the center of the particle, and that can drive fracture at the center of the particle, which propagates to the edges, or the opposite during delithiation. Here, in this case, you get tensile stresses close to the outside of the particle, which then propagates inwards. And so the fraction of broken bonds, or with different C-rate simulations, you can determine capacity loss and how that evolves with time. So it's a very practical model. You can develop reduced order models which fit into lifetime models and such from this. More recently, under the Fast Charge program, we've been tasked with understanding how material architectures, especially the polycrystalline architecture of NMC, contributes to cathode cracking and capacity fade in the cathode under Fast Charge. This is a common NMC 532 architecture where you see the different grains, individual crystals, and by mapping this together with FIB-SEM, Donald Finnegan, who came to us from Paul Shearing's group at University College of London several years ago, great guy to work with. He's working together with Professor Volker Schmidt. Donald's doing the FIB-SEM with electron backscattering to identify the individual grains, and Volker Schmidt is working on segmentation. So we have integrated this into an abacus cohesive zone model. It considers the anisotropic diffusion in each of these different grain directions. We have done a lot of work to have boundary conditions on the outside that represent Butler-Volmer conditions, as opposed to assuming uniform flux on the outside, because there's going to be preferential grains which have higher flux compared to other grains in the system. And so we have presently built this up in 2D. We've got it partially into 3D for smaller geometries, and can track a damage factor which describes the grain-grain separation and also the transport path damage. So this particular model is just some early results from this after constant current. We don't see much change in the damage factor at different C rates. That's because as you go to higher and higher C rates, you cut off sooner. But if you do continue into the CV range, then the cutoff is later and you do see some dependency on the damage. So we're working to both scale this up to 3D and validate this model, tune all the parameters. And soon thereafter, we hope to also go on to 811 high nickel materials, which have even more damage. Okay, in the Phoenix model, what we've done is to develop a continuum damage model. And so similar to kind of borrowing from the lattice spring model, it tracks a damage variable, which is 0 when undamaged, and then can transition to a completely damaged state. In this model, we've got anisotropic transport. We're working to include all of the realistic electrochemistry, such as the Butler-Volmer boundary conditions. Here we don't have the grain-grain boundary description of the cohesive zone model. So we'll be kind of curious to see how these two models compare and if there's, which one scales better and which one provides us a better description of the actual system. I believe this is a video. We'll see if this plays. So there's the concentration gradients in the particle. This is with uniform flux on the outside surface, so it's not quite the Butler-Volmer boundary conditions. And here you can see this plaid pattern depicts the different crystalline orientations of the individual grains. So where you see kind of just a line, that means that the grain is kind of, you're looking down the lattice, whereas when it's flat, you're seeing the face of the lattice. Okay, moving on to kind of some work that we're doing on the silicon anode. So following the KBAT program, which is now done, we've got just a small amount of funding to finish off the mechanical crush models. Our program managers are encouraging us to apply these models to emerging material systems. So we're starting some work with Stephen DeCayue on the lithium sulfur system that he mentioned. And for the silicon anode, we're working with a kind of consortium of different labs under two different programs, the Silicon Deep Dive and also the Siesta, SEI, ESTA is the Siesta acronym, understanding the side reactions that occur on the silicon surface. So definitely mechanical deformation is a problem for silicon, but also the kinetics of these side reactions, the SEI formation is perhaps even a larger problem. It's a very reactive system. Here we've been working with a macro homogeneous model. We tackled the mechanics first. We are not quite as constrained in terms of the description of the mechanics when you have a custom developed macro homogeneous model. So this is a large deformation mechanics model. And then separately, we're working on developing interfaces with with Kandler to describe the solid electrolyte interface chemistry. So first, going into the large deformation model, I think you're probably all familiar with silicon. Big problem is that you've got large capacity, that's great, but up to 400% volume expansion between a full charge and discharge cycle. And so over many cycles, it forms cracks in the material. Also, the SEI layer can be fractured and reform and thickens over time. We also see at the composite electrode level that the electrode thickens with each individual charge-discharge cycle and contracts, as well as it kind of permanently thickens over time. There's some sort of plastic deformation which occurs. We don't have the plastic deformation built into this model yet, but that's also something that we'd like to describe. And so, just kind of a cartoon of this is that these small particles, get much larger, and that causes the thickening of the electrode as well. Also, the material seems to become more porous over time. Both turns from a crystalline phase, if it started out there, to amorphous, and then also becomes more porous. So we'd like to guide cell design with this model. This is the work of Weijie Mai and Andrew Kolklaser, published last year, and he has started with finite strain theory to describe the large deformation mechanics. And this deformation tensor F here, it has a multiplicative decomposition. The Fe is an elastic term, and then the Fc is a concentration dependent term. Usually when you see small deformation models, these are additive. And in this particular case, for large deformation, these factors are multiplicative. So the concentration dependent deformation here has a partial molar volume term that you're probably familiar with from other works. And you can couple that together with porosity and such. There's a lot of constitutive relationships and different assumptions that go into this model to couple the various properties of the porous electrode to the deformation. And then another factor that we have is the Jacobian of the deformation gradient. This is something that turns up quite a bit in the governing equations, and I only have some small examples of this. But this Jacobian of the deformation tensor shows up differently whether you use an Eulerian conservation frame or if you use a Lagrangian conservation frame. And we've chosen the Lagrangian conservation frame. So as we have volume and expansion and deformation, we are not remeshing this, just the mesh itself expands. And that's described by this deformation tensor as well as the Jacobian. And so the governing equations, they end up looking pretty similar to the original governing equations, but with the Jacobian showing up in a few extra terms. The flux looks just a little bit more complicated. And I'd have to refer you to the full paper for the full description. It's quite a complex model. Weijie did a lot of work to build this up in COMSOL initially, which is kind of a flexible framework for testing out different physics and theories, ensuring conservation, and now we're working on building up a custom coded version of this same model. But some things that you'll see, if you have a very slow charge, C/50 rate, here all three cases show up similarly. What we've got is in black is the traditional P2D model with no volume expansion. And so the porosity of these three different regions stays uniform between the beginning and end of discharge. And so this is essentially what we've initialized the model to for, I believe this is the anode, the separator region, and the cathode. And for these other two cases, there's a really uniform expansion of the silicon anode that reduces the porosity, which was initially 50% down to just about 30% or a little bit less. And the expansion here, we have a fixed, I believe these are fixed boundary conditions. The expansion is taken up by the separator as well as the cathode. So those have to compress as the silicon anode expands. At the 1C charge rate, you start to see a bit of separation between these different cases. So here, another interesting thing is that the silicon anode has a non-uniform porosity. There's a gradient. The smallest porosity is close to the front of the current collector because the electrode gets used preferentially at that region. And that shuts off electrolyte transport at that region. And so with the volume expansion, you see different behavior. You also see a little bit of dependence of the open circuit potential on hydrostatic stress, and that's the difference between these blue and red lines, but it's really pretty minor. And so just to point out a difference from a traditional P2D model, which are the black lines here, versus this new large deformation model, as you increase the initial anode porosity of your design, a P2D model predicts that you want that anode porosity to be as small as possible. Our model predicts that there's some sort of optimal there around 45 to 50%. And similarly, as you increase in loading, the optimal loading for these cells is a little bit different. I believe this is probably at a 1C rate between what a P2D model would predict as well as the silicon model. So going forward, we'll look at pathways to incorporate side reaction chemistry into this model and damage, look at differences across different silicon systems. I have just one slide, which I'll skip over, but to say that we're collaborating with Stephen to develop the side reaction chemistry of the SEI, understand that spatially as well instead of lumped, and how that evolves with cycling. And finally, I'll skip to the system level length scale and talk about life prognostics models. And this is an area, there's so many different degradation mechanisms. No one, to my knowledge, has coupled them all into a physics-based Newman or some sort of electrochemical model. And so what we work with is kind of a reduced order model framework, which tries to tightly connect the data with the physics and only add new mechanisms as needed to describe what we see in the data. We are unfortunately stuck with collecting about 6 months of test data before you can tune this model. And I'll give a couple examples from this model. First, to describe some of the degradation that occurs all throughout the electrochemical window of the two separate electrodes. So here we have an example positive electrode, and here's a graphite negative electrode. As you go to high voltages, you can start to oxidize electrolyte at the positive. As you go to low voltages, it accelerates the rate of electrolyte reduction. Pretty much the entire operating range of the graphite here is within the reducing area of the electrolyte. So that's always occurring. Fortunately, it's diffusion limited and slows down with time. And then finally, you've got mechanical stresses, which fracture and isolate the electrode. And so just to observe how some of these different things track versus calendar time versus number of cycles, it's important to separate the calendar time influence and number of cycles influence if you want to extrapolate accelerated tests out to, say, a 10-year lifetime. These side reactions occur with calendar time. They're accelerated with high temperature and high state of charge. We also see that they are somewhat coupled with cycling, that if you deeply discharge a battery or sometimes operate at high C rates, that what we feel is going on is that it either disturbs the SEI layer or it increases the surface area of the electrode and accelerates these side reactions. Some other observations are you can track the electrode damage versus number of cycles. That definitely accelerates at low temperatures where you have diffusion-induced stress, especially at high C rates. We also see some damage occur that looks analogous to this at high temperatures and high depths of discharge. This is something I'm not exactly sure what the driving mechanism is. And then finally, if you do fast charging, you can certainly exacerbate other side reactions such as lithium plating and cause loss of lithium. And so what we've come up with is a framework of reduced order models. And so these are expressed in a state equation form and then also an analytical solution form or a trajectory form. And so, for example, this diffusion controlled reaction, and I apologize, this might be too small for you to see. Here we're tracking the rate of some state variable, or we're tracking some state variable is equal to a rate K times square root of time. And you can also integrate that as a state equation. Here you're integrating the time rate of change of that state variable versus the present state, x of t, and the rate. So all of these different equations are interchangeable between a state equation form and also a trajectory form. So what we do is we fit test data. Right now this is somewhat visual. We're working on machine learning techniques to automate the identification of these individual mechanisms. But you'll see things in data like this blue line. This is a cold temperature degradation where there's a real rapid drop-in, break-in mechanism. And so we can describe that with an exponential decay term, followed by perhaps some other rate of fade, which is slower. There's others like the purple here, which look like the square root of time, so we can fit that with the square root of time fade. Others that accelerate, like the red, we can fit with yet another model here. This accelerating cycling fade is this particular model. And this one says that the rate of, if you take your state variable to be, say, negative electrode sites, the rate of negative electrode site loss with each new cycle is inversely proportional to the amount of remaining negative electrode sites. And so as you have fewer and fewer negative electrode sites, that's going to accelerate your fade rate. So with that, we collect about, like I mentioned, 6 months of accelerated aging data, go through a procedure to identify the model at different temperatures, have Arrhenius formulas to kind of map out the rates of fade versus temperature, TOEFL equations to map out the rate of fade versus different state of charges or negative electrode or positive electrode equilibrium potentials, some empirical expressions like power loss to describe depth of discharge and C rate. And with that, you can have a model that runs complex scenarios as well. And so here's an example of trade-offs between if a residential energy storage system had no thermal management, it might last 7 years if you cycled it at 50% depth of discharge, whereas if you added thermal management, you could get it to last 10.5 years at 50% depth of discharge. And then if you cycled to higher depths of discharge on a day-by-day basis, how long that, that particular battery would last. I think in the interest of time, I'll kind of skip quickly through this, but we've done the same thing with the Eaton Corporation, identified a model for resistance growth versus about 25 different cell level tests. And that model compared well to separate pack level tests where we, in this environmental chamber, changed to a different ambient temperature once per month to represent a different season of the year. And so we had a much more complex aging scenario. And there's a similar amount of error between these two different models, about 10% error bounds on the resistance for each of them. And interestingly, we saw some seasonal dependence between the summer and the winter seasons, you know, kind of a up and down. So there's kind of a short-term memory and resistance. If you take an instantaneous measurement, it matters what you did to the battery more recently. Also under an RPE amped program with Utah State and Ford, Utah State developed an active balancing control system, which you could use to balance individual cells. So if there's a weak cell, you're no longer limited by the capacity of that weak cell. It does this with a 12-volt isolated bus, DC-DC converters at every single cell. However, a cost-constrained version of this, which Ford is now working on, would implement this on groups of cells, so more at the module level. So what this does is if you've got non-uniform degradation in your cells, you're no longer limited by the weakest cell. It's an expensive system, but we partially offset that by this 12-volt isolated bus also powers the auxiliary loads of the vehicle. And so you can get rid of a high voltage to 12-volt DC-DC converter that powers your headlights and computers and stereo and all those auxiliaries and replace it with this system. And so with that, we predict the system could potentially give you about 40% lifetime extension for an EV battery. It costs just a little bit more. There's some other benefits in terms of modularity of the control system that we feel are worth pursuing. So, and perhaps under very aggressive, like medium or heavy duty vehicles, a system like this could make sense. Like I mentioned, the Achilles heel of our present life prediction is it takes a long time and a lot of money to run all these life tests. So we're working on early predictors of lifetime. There's some great work out of Will Chu's group at Stanford. You've probably all seen. And basically, we want to match up the data to the physics models as closely as possible, describe the uncertainty in our models, understand which experiments drive down that uncertainty, and then also understand what sort of possible special tests that we can do to isolate negative, positive electrolyte changes, such as incremental capacity analysis, but also move beyond that with some special custom cell designs. So that's an active area for us. Just to conclude, in terms of opportunities, we don't work in education as most of you do. However, we do host a lot of visiting PhD students, postdocs, and also faculty from time to time. So this would be a great area for collaboration. In terms of the multi-reaction chemistry, I think this is an area we need to work together as a community. Cantera is a great building block for this. There's a lot of properties in those Cantera models, so the Newman model's hard, Cantera models are also going to be hard. So we need some theorists to help build in some of the missing properties there. In terms of the microstructure modeling, we now have some novel diagnostics experiments. I did not get to cover these at all, that are beginning to highlight the heterogeneities that are on the same level as what we're predicting in the microstructure model. And so this is an area where we're keen to compare models to the experiments and identify new physics, as Tom Fuller elaborated on yesterday. I think that's the interesting area of the models, is where you find about new physics. There's a lot of work to integrate electrochemical and mechanical degradation models, also build that up into lifetime models, and also for machine learning to identify both lifetime models as well as all of these properties here. So with that, I'd like to thank our sponsors at Department of Energy. We've got all of our publications should be up on this particular webpage, and thanks a lot for your attention. Thanks to the organizers, David Howie, and all your colleagues for the invitation for organizing this.
Thank you very much, Kandler. That's great. We really enjoyed your talk.